Well, I would like to begin by thanking all the people who made this possible. Particularly, I would like to thank Dr. Goins and Dr. Blackman, who kindly invited me to be part of this experience. We are going to talk about lower binomials, and this project was developed over the summer and as part of the MSRI UP program under the supervision of Professor Ardila and Dr. Rojas. Suppose that we have the following trinomials and we try to solve for the roots of this trinomial, and we know that for trinomials of degree 2 all the way up to degree 4, we have different tools, different techniques that can help us to solve this kind of problem. We can use quadratic formulas, we can complete the square, but it's easy to run into troubles when we have trinomials like this one. During the entire talk, we are working only with univariate trinomials with real coefficients, but of course, part of the project is to generalize the ideas that you're going to see two polynomials in general, but the trinomial case is interesting enough to be analyzed. Well, since we need different techniques, notice that one thing that we can do is the following. Assume that f has a root which is really small. In that case, the absolute value of that root, we can get rid of the first term because it's going to be really small, right? So in the neighborhood of x, the polynomial f is going to behave pretty much like that binomial over there. In the other case, for example, if we have a root of f which is really large, then we can get rid of this other term, and in a neighborhood of x, then f is going to behave pretty much like that binomial. Then a good idea is, instead of trying to solve for f, let's try to analyze what's going on with respect to these binomials associated to f. Notice that let's go even further. If we plot all the roots of f1 and f2, over there you are going to see the roots of f1 and f2, and if we plug in the roots of f, which are the red points, then you can see that these roots appears to be really close, right? Actually, if we take one of these quadrants and zoom in, then you are going to see that these roots indeed are really close. Of course, I'm not trying to prove anything with the picture. I'm just trying to offer some intuition behind this problem. We can do the same over the real edges, and the behavior is pretty much the same. But why binomials? Well, because for binomials we can play around with Euler's formula, and we can find an explicit way to solve for binomials. So the idea basically is, once you have a trinomial, we transform the problem of finding the roots of a trinomial into problems, finding the roots of two binomials, and we know how to solve for binomials. In order to attack this problem, we need to borrow some tools from polyhedral geometry, and I will try to avoid defining anything formal. I will take advantage of your intuition, because actually these kind of things are very easy to visualize. Let's define first what is arch node of f. Given a trinomial f, arch node of f is basically the convex hull of those points over there. Notice that the first coordinate is basically the exponent, and the second coordinate is minus log of the absolute value of the coefficient. So it's going to be something like this. The convex hull, I won't define what is the convex hull, but imagine that you have a rubber band and you put that rubber band around those points, then the area enclosed by that rubber band is going to be precisely the convex hull associated to those points. And that is going to be arch node of f. Notice that it is not hard to see that these are all the possible cases. Once you fix the extreme points, then we are going to have either of these cases depending on the location of the middle point with respect to the line that goes through these 2 points. And also it's interesting that at some point we'll start generating, random polynomials, right? And when we generate random polynomials, then the arch node of f are going to be a random point on the plane. So we can get rid of this case because this case is going to happen with probability 0. So the only possible cases are case number 1 and case number 2. In this case, the vertices are exactly those points over there, and the edges are, well, the edges, and we're going to call lower edges to these edges right over here. Okay?
Your trinomials always have real coefficients, is that right?
Always have real coefficients, yeah. And that's the, okay. And lower binomials are going to be precisely the binomials induced by these lower edges. Notice that each lower edge is going to be associated with a binomial. In this case, for example, is going to be C0 plus C2 x to the A2. Or we can have this other case when we have two lower binomials that are F1 and F2. This case, as I said, we don't care about that case. In that case, we don't have any lower binomial. And notice that it's easy to discriminate between these two possible cases. We just need to find a nice condition like this one to know whether the point in the middle is above the line or is on that line between the two extreme points. And we are going to call this condition flatness condition. Well, just to wrap up everything, remember that once we have a univariate trinomial f, then we have two possible cases. If f is greater than 0, then we are going to have one lower binomial, which is the one defined by the extreme monomials, and the other possible case is when we have two lower binomials and are precisely the one defined by the first two monomials or the second two monomials. And remember the case that we start analyzing, this case of x to the 39. In this case, the lower binomials are precisely f1 and f2, and for that reason we got nice things and nice approximation between the roots of f and the roots of f1 and f2. As part of this project, we went into two directions. The natural question is the following. Well, this term persists, meaning that given a trinomial f, if you compute the root of the lower binomials, these roots are always going to be good approximation, whatever that means, of the roots of the two roots of f. And the second question, we're not going to talk about the second question for the sake of time, but it's another interesting question, and is whether the number of positive roots of f is exactly the same as the number of positive roots of its lower binomials. Okay, approximations. Always when we try to approximate the roots of a polynomial f, a trinomial in this case, of course we are thinking about Newton's method. If you don't remember Newton's method, the formula is over there, but the basic idea is that you start with the guess, you plug in the guess into certain functions, and you start getting approximations of true roots of f. Sometimes you converge to a true root of f, but sometimes you don't converge. And one of the things about Newton's method is that it's pretty messy in the way that this convergence happens. Sometimes it converges, sometimes it doesn't, and we don't have and we don't understand this convergence region as well. What is a good approximation? We are going to define a good approximation in terms of this convergence. Basically, a good approximation is going to be a value that as soon as you start using Newton's method, you start converging quadratically to a true root of f. That is the formalization. Notice that in this case, what we are saying is the following. If you start with C0, then each step is cutting the distance between the approximation and the true root by halves. So if we are working, for example, in a binary expansion, then each step you are ensuring that you are getting at least one digit right. And fortunately, we have this nice theorem, which is part of Smel's work in the 80s. And the theorem basically says that whenever you have a function and certain approximation, that approximation is going to be good is going to be a good approximation in the sense that we defined before if this function alpha is extremely less or equal that value over there. Of course, I didn't define alpha because we basically use smell theorem as a black box. Basically, we start analyzing the root of the lower binomials and plug it in using this smell function to see whether these roots were not good approximation of the roots of f. And we start plotting on the sphere. What does this mean? Well, this means the following. We fix exponents a1 and a2, and we start generating random coefficients. In this way, we start having points on the sphere once we normalize all these coefficients. In this way, we can associate each point on the sphere to a specific polynomial. In this case, green is good and red is bad, in the sense that a green polynomial is one that at least one root of its lower binomials is going to be a good approximation to the roots of f. In this case, notice that not all the time that is going to happen, but the thing is the following. Probably the condition of being a good approximation is pretty restrictive, in the sense that we're forcing to that good approximation to, as soon as you start using Newton's method, you start converging quadratically. But probably you can like double around for a while and after that converge quadratically. So a good idea could be, let's try to do the following. Take one of the roots of the lower binomials, right? Try to see if it's a good approximation. If not, try applying Newton's method at least one step. And after that, check again. And what we had was the following. Just applying one Newton step, all the cases were good, meaning that at least one root of the lower binomial was a good approximation in the sense of Schmel.
Why does your picture look like Stefan's picture?
It's a universal truth.
It's a universal.
Sorry, can you say a little bit more about why this is a sphere? So what are the different dimensions, axes?
Well, in this case, we don't care much about the dimension. Remember that what we're doing is the following. We fix exponents and we start generating random coefficients, right? Once we normalize these coefficients, then we can associate each polynomial to a point on the sphere. And this was just a way to visualize what was going on.
Right.
Of course, sometimes, for example, if we run like a million cases, probably we have like a tiny red dot over there saying that this is not true. But this was just to visualize and to have a sense of what was going on.
What's the black?
The black were point that we didn't try.
Oh, okay.
Yeah. Just
So is each of the green dots triplet formed by the random coefficients of the trinomial?
yeah. And these coefficients were randomly generated using random distribution. Actually, one of the purpose of the break is try to analyze this using different distribution like Gaussian distribution. Any other question? Well, and we have precisely this conjecture that we couldn't prove in 6 weeks, but this is a work in progress, and it's precisely that after 2 Newton's iterations, at least one of the roots of the lower binomials is going to be a good approximation of the roots of f. Upcoming goals. Upcoming goals is proof conjecture number 1 and conjecture number 2. I didn't mention conjecture number 2 because we didn't talk about the second problem for a matter of time, but I believe that I have time. Do I? Oh, perfect. So we can talk about problem number 2. How often the number of possible roots of lower binomial equal the number of possible roots of f? Well, just to establish some notation, in here we're considering the different octants, and each octant can be associated with a different distribution of sign. The first octant is going to be the octant with signs positive, 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 and we are going to use this sloppy Descartes rule of signs. I will explain why sloppy. Well, in this case, notice that Degas rule of science, what Degas rule of science says is that the number of possible roots of a polynomial is either equal to the number of signs different between consecutive terms, or is this number minus an even number, right? It's sloppy because notice that if we are going to use Degas rule, we need to establish an order for the monomials forming part of this polynomial, but we are going to assume that always we are going to list all the terms of a polynomial in an increasing way. And well, the question, when the number of positive roots of the lower binomials are going to be equal to the number of positive roots of any trinomial f. We start doing exactly the same. We fix exponents a1 and a2, we start generating different cases, and we check whether this number of positive roots were exactly the same. Green means good, red means bad. And this region is really interesting because first, 94% of the cases were a success, and we start trying to do some probabilities over this sphere. The natural question is, okay, if you take a random polynomial, what is the probability that the number of positive roots of that polynomial is exactly the same as the number of positive roots of its lower binomial? And since we know how to compute the surface of the sphere, this area, we just need to somehow try to compute this red region, or at least trying to estimate that red region. The first thing that we did was to prove that this region was always enclosed by these two curves. The first curve, the white curve, is the Flanders condition. We already talked about the Flanders condition. And the second curve is a pretty interesting curve, which is called the discriminant variety. This discriminant variety, this is just a fancy name, discriminant variety, but it's precisely what the discriminant variety gave us are all the polynomials with multiple roots. So this red region is always going to be enclosed between these two curves. The next step was trying to see where these points were located in each of the octants. And we played the following game. We said, okay, let's take, for example, the following polynomial with all the positive coefficients, right? And the thing is the following. Notice that this polynomial doesn't have any positive roots, right? Because all the coefficients are positive. And for either case, if the lower binomials is this guy or this guy or this guy, it doesn't matter because it's also a polynomial with positive coefficients. So in that case, neither of the lower binomials are going to have positive roots. So all the cases in the first octant are good. So this red region is never going to intersect the first octant. But if you take, if we can go further, if you take, for example, any octant with only one sign change, it's going to be the same. For example, consider minus plus plus. If you take minus plus plus, then using the Degas rule of science, it says that the number of positive roots is either the number of sign changes, which is 1, or 1 minus an even number. But this second case, 1 minus an even number, is impossible, so this polynomial is forced to have one positive root. If you take any possible lower binomials, you are going to have exactly the same. So the only trouble octants are the octants with 2 sign changes. Minus plus minus, plus minus plus. So since only 2 octants are the trouble octant, then the probability is going to be at least 75%. Because you can get rid of 6 of the 8th octant as octants that this red region is never going to intersect. Here is conjecture number 2. Our conjecture is that the probability of choosing a random polynomial with the same number of positive roots as its lower binomial is going to be 91.7%. Where this 91.7% comes from? The idea is the following. Notice that this red region, we proved that always is going to be enclosed in one of the octants. This red region never can cross across the planes xy or yz, and in that case we can play inside the the octane in the following way. We can cut across the 2 points which are the string of this red region, and we can save at least 1/3 of the octane. And if that's the case, and we can do that, then the probability is going to be precisely 91.7%. Future work, as I said before, is, well, proof conjecture number 1, proof also conjecture number 2, but this is still a work in progress. Also, as I mentioned, we would like to extend this using different distribution as Gaussian distribution. And I would like to conclude by thanking Dr. Ardila, Dr. Rojas, MSRI, and NSF and Sloan Foundation that kindly support us during the summer. And again, thanks Dr. Goins and thanks Dr. Blackman for inviting me. And thank you all for coming today.
Are there any questions for our speaker?
Question. I'm curious about the red region that you had before, towards the end here. And when you mentioned the discriminant variety. So it seems to me that that red region is a little bit too smooth around the edges just to be kind of a random phenomenon. And I'm guessing that you could probably say that that region is cut out by a set of polynomial equations. That should be some type of an algebraic variety. So do you have any idea kind of what those equations should be as a function of the exponents that define the trinomial?
Yeah, we actually have the actual equation of this curve. Is a really nice curve, and it's a pretty well understood curve. And actually, the fact that this red region is going to be enclosed between the flatness condition and this discriminant variety is a well-known fact in the field. Okay. Yeah, but it's a really nice curve defined by Selevinsky, I believe. And yeah.
Can there be only one red region, or can you have two?
We actually are going to have 2 red regions. Actually, one of the things that we can prove is that bad points are going to be always across each other. Because notice that once you plug in, let me think about it. Yeah, consider that you have a trio of coefficients, and those coefficients define a polynomial which is a good polynomial. If you take minus C0, minus C1, and minus C2, then you're going to be exactly the same because you can always factor out the minus, and you're going to be also a bad case. So these regions are always going to be across each other. Yeah, we're going to have 2 outcomes all the time, which is good because then we only need to take care of one of the regions, because most likely using this symmetry we can always multiply by 2, and we are going to have a pretty good sense about this. I don't know if that answered your question. Yeah.
So then maybe if I can ask a follow-up to that. So then it seems to me you have the 3 coefficients that are 3 real numbers, and you don't really care about what happens up to scale, kind of what you're saying. So you kind of scale the coefficients. It's basically the same trinomial. So you're really dealing with the projective plane, the projective real plane, which isn't really the sphere, some nasty non-orientable manifold. So has you thought at all about maybe like a slightly different way of visualizing what the space could be? Again, it's not going to be a sphere. It's almost like a Mobius strip, but it's something nasty.
No, I haven't. But that's a good idea. Probably I should.
Okay, we can talk about it.
Yeah, that's a good idea. Thank you. Yeah, question.
I'm just curious about your motivation for undertaking this kind of study. When you just started, first I saw the trinomial you put on the board, and I wanted to run out of here. So, what motivated you to just do this? I'm just curious about that.
Oh, well, actually, this is not my intuition talking. This is Mauricio Rojas' intuition talking, which is an expert on this field, and he guided us during the summer with respect to this problem.
Okay.
Yeah, so the intuition is not mine, so the answer is I don't know.
Okay.
Yeah, I didn't came up with this idea. It was all Mauricio.
So, something, if in case you're interested and have copious free time, there's a mathematician whose last name is pronounced Thue, but it's Thue. It looks like Thu, but it's Thue.
Okay.
And he is responsible for some equations and problems that look a lot like yours, but instead of setting it equal to 0, you're setting it equal to plus or minus 1. And there is a lot of study on questions like these with 2A equations. And I would be kind of interested in how your results compare to those. So just thought I'd mention it for you.
That's great. Thank you. And actually, I have a question for the audience. I know that usually you are the one making the questions, but the thing is that this problem is really hard to me because at least I'm not aware of a lot of results involving Newton's convergence. I know about this smell theory, but I'm not aware of any other results that can ensure me that once I have a rule, that rule is going to be a good approximation if I use Newton's method. I don't know, you know, or you can point me in the direction of someone who's working on this or some literature.
I can say right off, in general, Newton's method doesn't really work too well because you do have to worry about two things. Number one, where your starting point is and how close you are to the actual value, because you could be so far away that you'll never actually converge to what you want. Second thing is you have to worry about whether you have repeated roots and when the derivative is equal to 0. And I think that your trinomials are set up so that in some sense you don't really have to worry about that. Well, that's the discriminant variety type of idea. But really, if the derivative vanishes, then you're totally out of luck. It's not going to work. I know that in general what people do is these optimization techniques. And sort of the idea is that you don't really want to find roots using Newton's method. You basically say something to the effect of there's some type of a function and you want to try to minimize this function, and ideally the minimum of that function should be 0. That's sort of finding the roots. But you want to try to get it as small as possible, and the method of finding the smallest one is pretty much the generalization of Newton's method. So more or less you have to find somebody that works on optimization techniques, and they can certainly tell you what's the right way to go.
Thank you. Great.
How are those coefficients drawn for your 91.7% projection?
I'm sorry, I didn't hear you.
And how are they drawn? Probabilistic method. Uniform and so on?
Oh, uniform. Yeah. Uniform, I mentioned that these coefficients are uniformly generated, and one of the future goals is trying to generalize everything using also Gauss distribution, for example, using different distributions.
Uniform, they're assuming they're just real numbers, right?
But you normalize.
Okay, uniform on the sphere.
Yeah, exactly. Once we have the coefficient, we normalize and we start having points on the sphere, yeah.
It's just by chance, I think I maybe missed this, as you were getting your approximation, how were you telling how good that they were? Was some measure that you were using to tell how good your approximations were?
Yes, actually, we define a good approximation using this smell function that ensures us that once you start using that approximation, it's going to converge quadratically to a true root of f. Yeah. Basically, Schmel's alpha theory is the measure that we have to see if an approximation is good enough.
Okay.
Yep.
Because these were polynomials and you can control the coefficients a little bit, it'll almost make me run to the computer or something to test a few to find the real roots and all that stuff. Did you do any of that by chance?
I'm sorry, I didn't get that.
Did you use any type of computer algorithms that find
Yeah,
actual
yeah.
numbers?
Indeed, we implement our Mathematica of this algorithm to determine whether the root is a good approximation. Because the thing is that once you have a good approximation, you can always apply Newton's method and you can get as close as you want to the true root of f.
Thank you.
Any other questions? I'm sorry.
Are there any more questions?
Great
Well,
job.